Xerox Innovation Group in Webster, NY, and most recently in the position of principal scientist and project leader. His research interests include data analytics, cyber physical systems, signal and image processing, computer vision, and medical security, areas in which he has 54 patents and has authored over 220 journal and conference publications. He served as the editor-in-chief for the IEEE transactions on image processing from 2018 to 2020 and for the Journal of Electronic Imaging from 2011 to 2015 and currently serves on the editorial board for the proceedings of the IEEE. He is a member of the IEEE Publications, Products and Service Board and chaired the IEEE Conference Publications Committee in 2017-18. He is the editor of the Digital Color Imaging Handbook published by CRC Press in 2003. Dr. Sharma is a fellow of the IEEE, a fellow of SPIE, a fellow of the Society for Imaging Science and Technology, and has been elected to Sigma Xi, Phi Kappa Phi, and the Phi Mu Epsilon. In recognition of his research contributions, he received an IEEE Region 1 Technical Innovation Award in 2008. Dr. Sharma served as a 2020-21 Distinguished Lecturer for the IEEE Signal Processing Society and is a recipient of the 2021 ISNT Raymond C. Bowman Award. With this, I want to invite Professor Gaurav Sharma for the talk on multimedia signal processing and machine learning for music analytics. Sir, with your permission, we want to record the session also.
Yes, that is fine with me. And thank you, Chirag, for the kind introduction. And good evening, everyone. I think, and welcome to this session. So today I'm going to be talking about some of the work we've been doing in collaboration with others in the area of multimedia signal processing and machine learning for music analysis. I think this is illustrating quite in line with the theme of this winter school of multimedia signal processing and deep learning. So before I begin, I'd like to acknowledge the work I'll be presenting is largely the work done by along with my collaborators. In particular, Bo-Chen Lee was a PhD student at the University of Rochester. He has since graduated, and he was involved in almost all pieces of the work and also driver for some of the key parts. Professor Zia Duan is a colleague at the University of Rochester, and the work has been done collaboratively with his group. Xinhao Liu was a master's student. She's graduated. And Karthik Dinesh, who's currently a PhD student in my group at the University of Rochester. So I'd like to acknowledge the work is really reflecting their contributions in this case. Here's an outline for my talk. I'll begin with an overview and motivation, which gives a highlight and motivation for why multimedia signal processing and machine learning for music analytics. And then I'll talk about some sample projects in this area that we worked on. And then finally, end with some conclusions and emerging directions. To keep this interactive, maybe we can have questions as we go along. So people can probably not ask questions directly, but you can chat them to Chirag, and Chirag can interrupt me and ask questions. I will not be able to keep track of the chat at the same time while I'm speaking, so somebody else will be keeping track of the questions as they come. But feel free to ask questions as we go along. Okay. So I think we're all familiar with music, and audio devices have a long history and technology progression. In 1877 is when Edison introduced the phonograph for production of music. And after that, there was also the vinyl recording. This is what we're familiar with as vinyl discs. They're actually enjoying re-emergence and re-emergence of popularity in this type of media. Increasingly, people are buying these vinyl discs again. 1962 was when the compact cassette was introduced, which became sort of the mainstay for people to record their own music and exchange with others. And then 1982 was the emergence of the compact disc from Philips and Sony. And in 1997, a relatively unknown company, Seihan Information Systems from Korea, introduced the world's first MP3 player. So there's been a strong progression of both technology and innovation that has been driving this. In particular, the MP3 player was based on a technology for compression of audio, which enabled a lot more songs to be stored in a small memory footprint compared to what was previously feasible in this case. So this makes us think that audio is the primary form for music, which is partly true, but music does not consist of audio alone. There is also a strong component these days in musical performances having to do with videos. So video streaming services are increasingly popular. They're either directly services for streaming video or things like YouTube, where there is most music available in the form of videos accompanying them. And also there are specific video festivals which are focused on music. Research in the psychophysics community has indicated that this plays an important role, that in addition to the audio, the video plays an important role in communicating meaning and emotion in music. So music is not simply at current point in time, music is not simply an audio form of signal, but also involves video. And if you think about it a bit more, there are also other modalities that come into play in music. In particular, if you consider classical music and things like chamber music and orchestra music performances, then you can think about what are the different modalities that come into play. So this is from an article that we wrote for the Signal Processing magazine sometime not too long ago. That's where this image is taken from. And you can see, if you think about it, then there is the audio modality. So these are a bunch of musicians performing different instruments. They have the audio modality for which I'm showing you the spectrogram. So this is a distribution of the spectral power distribution as a function of time. On this axis is frequency, this is time. So you can see that this is what people are most familiar with and what people think about when they think about music. But you've also got recording of the video, the artist performing. And from that, you can think about a variety of information sources that can become available to you. So as you see the hand movement correlates with specific instances that you see in the music. So over here you're showing that the key strike is showing strong onsets in the spectrogram of particular spectral components corresponding to the piano. Similarly, if you look at this for the violin, instances when the player is moving the fingers on the strings, they're using that to modulate the pitch to create something known as vibrato, which is a form of artistic expression, which makes it much more lively and expressive compared to just playing the instrument without introducing this variation. And not only do you have these video and audio modalities, but for classical music, you also typically have the score. This is the score, which is the description of the music and the composition. So the score is what will also correlate with when the musicians play different instruments or different notes on their instruments. So in terms of analyzing music, if you think about analysis purely based on the audio modality, you're not using the rich sources of information that are available to you. You have information available not only from audio, but also from video and from the score. So as a form of a signal, current music performances are very well suited for multimedia signal processing by combining analysis across the different media types and also machine learning for integrating the information that you have from these different modalities. So while traditional music analysis has focused on the audio modality alone, increasingly there is interest in trying to do joint analysis of the multiple modalities for music, and this can be much more effective. And that's what I will try and illustrate in my talk here. So you want to look at both combination of video and audio and analyze these in conjunction to figure out what is going on in the music. Now, this can not only give you greater power for solving existing problems by doing this jointly with the multiple modalities, but also creates new opportunities. And I hope to highlight both of these in my talk. And this is a very nice playing field for multimedia signal processing and machine learning, because as I already mentioned, as an art form, the art form is already multimodal, providing you a set of multimedia signals for analysis. And in terms of integrating these, modern machine learning techniques provide you good ways in which you can integrate these into a coherent whole, rather than relying on individual signal analysis by itself. So here's an example of what I mean by this. So if you were to imagine, this is showing you a chamber music performance with a set of musicians performing different instruments in coordination with each other according to the score. You have video available in this case, you have audio, and you also have the score. So in traditional analysis, the video has not been particularly emphasized in the analysis of the audio. Often, a task that people are interested in is trying to separate the audio into the different tracks corresponding to the different musicians. This, however, can be enabled much better if you can figure out what instruments are playing at different points in time. Here is this new problem which arises, which is the problem of source association. So you have the players, you can identify the players through analysis of the video. That is something which modern machine learning and deep learning in particular can enable. And I'll talk about how that happens. Once you've identified the musicians, you can then also identify what streams correspond to them. So in the audio, if you separate these into individual streams, you can also associate each of them. What's the advantage of this over analyzing purely the audio? So a particular musician is not playing at a particular point in time, even though they may be both using the same instrument. So maybe two of them are both using the violin. When one is not playing, you know that the audio stream should only be associated with this person. This really makes it much more beneficial, not only for source association, which is the problem that I said is a new problem that arises in this multimodal data set, but also for separation of the audio stream into the different signal streams, which is a problem people have been working on for quite some time, both for speech and for music. You may have heard of the problem in the speech context of source separation, where you have the problem of mixture of a number of speakers. It's commonly called the cocktail party problem, where you have a number of speakers speaking together and you have the audio tracks recorded and you would like to separate them into the individual tracks. So this is the music analog of that for chamber music performances. And the key benefits that you get is that you introduce new tasks over here. The new task is the one of source association. That's not something that you have in an audio stream alone. And they also enable improvements in your traditional task of source separation, which is the one of separating these into the different signal streams over here. Now, this does involve a number of new signal processing and deployment of known signal processing techniques. In particular, if you look at the video performance, the way it's recorded, you will have the video performance, you will have the audio, and these typically are temporally aligned. The video and the audio are aligned in the signal. This is what you will find in most videos. However, the player and track are not associated. There is no association between what player is playing and which track this corresponds to. Same with the score. If you also have the score corresponding to this performance, you do not have the player and track aligned or associated with the score. And association also does not exist between the score tracks and the audio streams. So you have a number of new problems as well as a number of old problems that you're interested in solving in the space. So how do you start work on a problem like this? Well, the first thing you need is some sort of data set, which will allow you to both evaluate this in a realistic setting and also give you ground truth, which you can use to assess how well you're performing. So when you first started to work in this area, our first task was to actually create a data set. And this is what we refer to as a URMP data set. This is which was published in the IEEE Transactions in Multimedia. And this is specifically a chamber music performance data set for multimodal music analysis. So chamber music is what you saw over here, classical music performances with a small number of musicians with different instruments, and some of them could be using the same instrument also. So what are the objectives in putting together such a data set? You want a data set suitable for development and testing of multimodal analysis algorithms. That was the key objective. Rather than something which was purely audio, we wanted the data set to be inherently multimodal. And so you've got the challenges that you want to record multiple musicians and modalities on their different instruments, record audio, video, or as well as have the score available. And a key requirement is to have ground truth available, because if you want this to be a data set to be used for evaluation of different techniques, then you want to have the ground truth in which you have separate audio tracks, meaning for each of the musicians, you want to have an individual track. Whereas if they're performing in collection in a concert, you would only get the combined track. You would not get these individual tracks. So this was a key requirement, to be having separate audio tracks. Also have video and score associations with these tracks. This requires alignment between the score and the video, also between the score and the audio, and to associate how these align with this. At the same time, so this could be done pretty easily by taking individual musicians performing differently, different pieces, and putting them together. However, at the same time, you also want realistic and expressive synchronized performance. When musicians perform collectively, they synchronize with each other and rely on cues from different performers in order to ensure that their timing is right. And also they will introduce variations, minor variations in the score and how they perform, which is their own form of artistic expression. Okay. And I'll highlight that. In particular, vibrato is one effect which relates to that. Okay. And finally, we do want to maintain high quality audio. So what challenges does this pose, and how did we address those? Before somebody wants to annotate, okay, so I will approve annotation for who has requested annotation. Right. Oh. So I'm not sure. I've not used the annotation tool before. Okay. So as I mentioned, we wanted a multimodal, multi-instrument data set. Not used this annotation tool before, really. Okay. Ultimately, the data set we created ended up having 44 Western classic chamber music, ranging from duets to quintets. Individually musician performances, there are 149 different tracks in this. This includes instruments of different types. I'm not sure what's happened to my mouse. I've not used this annotation tool previously, and I'm not sure what this is doing. I apologize. Hello, can you hear me? Hello?
Yeah, sir. Yeah, sir.
Okay,
Yeah, we can hear you.
Yes, so something has happened. I received an annotation request from someone. I accepted that, and now I don't see my mouse. Oh, okay. See this? I see the mouse. Okay, now it's become visible, but I don't see the mouse. I only see.
Is it okay, sir, now? Gentlemen, please
okay.
disable annotation request by
Okay.
participants.
Can you see my mouse? Can you see my mouse, or people cannot see my mouse?
Yeah, sir, we can see. We
Okay.
can see your mouse.
So I will just use the mouse for pointing rather than rely on the annotation. Okay. So you
Correct.
can see there are different types of instruments. There are the string instruments over here. There are the woodwind instruments, and there are the brass instruments. So there were these combinations of different instrument types. Each track is individually recorded and assembled together. So this was on a sound booth, is where the musicians would perform, and they're performing a single instrument. We are taking those single recordings and then assembling them into different pieces, depending by combining the different musicians who performed according to a single score. So let's say you had somebody performing on the violin and on the cello, two sort of string instruments, and they had a single piece that they performed. They performed individually in the sound booth, but then we assembled that into a piece corresponding to duet. Similarly, you could assemble three musicians' performances into a trio, 4 into quartets, and if there are 5 of them, into quintets. So this allowed us to create a fairly diverse data set from a relatively modest number of tracks. From 149 tracks, we could create these 44-piece arrangements that are comprising of duets, trios, quartets, and quintets in this case. and a variety of different instruments. In some cases, the pieces have the same instrument performed by multiple performers playing different parts of the score, which creates this phenomenon of polyphony, because those instruments are harder to distinguish based on purely their spectral characteristics. Now, I described this. It sounds fairly easy, except that in order to get a realistic performance, when each musician is performing by themselves, is really quite a challenging task. If you're used to performing music in coordination with other musicians, then for you to give a realistic performance when you're performing by yourself in a sound booth is a totally unreal experience, unnatural experience. So how did we overcome that challenge? So this is illustrating the process over here. So I can clear the annotations. Okay. So this is illustrating the process. We first selected a set of pieces, recruited musicians to perform those. In particular, the University of Rochester has the Eastman School of Music, which is one of the leading schools of music in the Western music tradition. So from there, we recruited several musicians to perform for us, and then recorded what was to guide them and synchronize them. We recorded a conducting video. So this was somebody who conducts a concert, but the conduction they did to start with was just the video for the conductor, along with a single performer recording this on the piano. This was just to provide synchronization and sort of naturalness in this process of recording the individual pieces. The players then recorded the individual pieces in the sound booth while watching this conducting video. So that keeps them all synchronized because they're watching the same conducting video. And the melody also helps them synchronize to a finer extent compared to what is possible with the video alone. So this is what was fed to them through the earphones. They were listening to the melody, piano melody, recording from the conducting, and watching the conductor video, and then recording their own performance, which was recorded in high quality audio along with the video. So you had both audio recording as well as video recording the performers. Then you align the audio and the video because these are recorded separately. The video recording was not, the audio accompanying the video recording was not that high quality as we wanted. So the high quality audio was aligned with the video to create this video and audio track for this particular performer. This was annotated individually. You did background removal on the video to create just the performer themselves. The pitch was annotated for this individual performer by analyzing this individual signal, which is a relatively easier task. And then we introduced a concert hall background and assembled this into a video. This is showing you for a duet with two performers. The second part was done exactly for the second player also. So this process gives you much more sort of realistic and expressive performances. Things are synchronized because of the conductor. You could also use, and we tried a number of different options in order to get the synchronization. We also tried a metronome. A metronome is something which you can think of as a clock, which is giving you a periodic signal. That did give us synchronization, but did not give us a very natural performance. So this was, after considerable trial and error, is how we came up with this technique. And this worked quite well and effectively and gave us realistic, expressive performances. So here's an example of a piece from this. I will try and play this. Hopefully you can hear this. So these are all string instruments. And you can see that this is close enough to what you can expect if you had recorded them all at the same time in a concert, because they were all watching the same video with the piano melody. They are synchronized and at the same time can also have their own individual variations in this process. Maybe in this time I will skip the details.
So is there any audio in this one?
Yes, there is audio. So you cannot hear the audio?
Yes, we are not able to hear.
So can you not hear the audio? Oh, okay. My apologies. Hello, can you hear me?
Yeah, sir, we are not able to hear. You have to sir play once again, and maybe your computer sound is muted or something like that.
Okay. So could you not hear the audio?
Sir, your voice is coming, but that
Okay.
audio of this particular recording is not.
I just, okay.
We are not able to hear it.
I should have checked that before. My apologies. I did not. Yeah. So I don't know whether we want to try and figure
Sir,
out how to. Yes.
this video is in any browser.
This video is embedded in the PowerPoint itself. This video is embedded in the PowerPoint itself.
If you have a link of this video, you can just drag this into any browser,
Okay.
so it will run.
Okay. So rather than try that real time, okay, I have a link of this video. Drag it into a browser and run. Okay. All right. And then though you will be able to hear the audio.
Now, let's
Will you
see.
be able, Will you be able to hear the audio if I do that?
No, just now no audio.
So I'm
Maybe,
going to
sir,
try and-
just to embed it into the any browser.
Yes. So I'm going to try that right away to see whether I can put this into the browser. So and then let me pause this and let me share my entire. I'll share my screen rather than share just a window. Still. Where is my WebEx window? There is the WebEx window. How do I get to share everything? WebEx does not show as an application. How do I get to WebEx? There it is. I'll stop sharing and I will share my entire. Is there a way to share the entire screen?
Yeah, so we can try in that way also.
Okay. So let me. I don't know if there's a way to. Does it give me the option of share screen one? Or what is screen one? Okay. Let's see if I can share screen one. Can you see the?
Yes, sir.
Okay. Okay. Now can you hear the video now? Can you hear the audio now?
Not yet,
No,
sir.
sir.
No. Okay. All right. So this is what I did. I pulled it into a browser, but yeah. So sorry, somebody was giving some hint in the chat. Please
Yeah, with
unshare and-
optimized. Yeah, so with optimized audio, there is some setting.
Okay. So let me.
You have to go in audio and video option
Okay. So
and
stop
speaker and
sharing.
microphone setting.
Yes.
In that one,
Share
sir,
screen.
WebEx
So
Smart
stop
Audio.
sharing and then I share with. So share with.
Sir, go into the audio and video.
Optimize for motion and video.
That's the
Is it?
fifth option, audio and video.
Okay. And
In
what
that,
should I-
sir, in audio particularly optimized for my voice.
Oh, okay. Audio and
And
video.
third one is music mode. So either of that can work.
Video settings.
It mentions others hear the original sound when you play an instrument or sing. Maybe third is a better option.
Okay, let me see if I can. My apologies. We should have tried this earlier. Most of my talks do not have audio in them. So WebEx Smart Audio settings, is that right? WebEx Smart Audio settings. Oh, music mode. Okay.
Yes.
Okay. All right. Yes, I've found that. All right, so I've set that. All right, so I've set that to share that, and then now let me see if I can share again. Okay. So can people, let me see if I can play it. So it should be from the slideshow, one slide. Can you hear it now?
Not yet, sir.
Okay, so then let me not try and
Yes,
do
we
this
can skip
online.
it, sir.
Let me just okay. So my apologies, but yeah, most of my talks do not involve audio, so I did not think about this in advance. Apologies. Okay.
Okay, sir.
Right. So what do we get as a result? And the end result is a realistic multimodal data
Hello, sir.
set. Yes. Hello. Can you hear me?
Sir, I am audible. Sir, I am audible.
Hello. Yes.
Hello. Sir,
Yes.
once you share at the new screen pop up, and that screen you have seen the top right corner, the one button is there.
Okay.
You
The
just
annotate.
need to click once.
Okay. Annotate. Annotate. Is that right?
No, no, sir, no, sir. Please unshare the screen.
Okay. Stop sharing. I stop sharing. Okay.
Share. Press the button share screen.
Share.
One pop up is open on your screen.
I did not see
Right.
the pop up yet. I did not see the pop up yet.
This new screen, small screen
Yeah,
is
yes,
open
that's
once
right.
you
New screen.
share.
That's right.
At the screen, you will find one button at the right hand side.
Okay. I see a button on
You
the
just
right hand side
press
which says
on.
automatic optimize or
Yes, yes, sir. That's that button.
and what do I say? What do I say?
Please
Optimize
click.
for motion and video?
Yes, sir. Please click on that button and now share
Okay.
your full screen.
Okay. And do you think now the video will be audible? Do you
Yes,
think
yes,
the
sir.
audio will come now?
Definitely.
Okay.
Yes, sir. Definitely.
Can people hear it now?
Yeah.
Okay. Thank you. So the key point I'd like you to observe in this is that they're synchronized while still maintaining the naturalness of the individual performance. I think that's probably enough sample to give you this idea. But the end result is we have a realistic data set. It's close enough to what you can get with people performing together while providing ground truth. It's multimodal. We've got video, we've got audio. It's diverse. We've got a variety of instruments. It's also rich. We've got a variety of pieces. We've got 44 different pieces assembled from this. So the final data set includes the assembled video performance, the music score, both in MIDI format and readable PDF format. There's the mixed audio track, which is the combination of the audio track, and the data set is freely available on Dryad. This is something which is the DOI for this data set. It includes ground truth with the individual tracks, which are annotated for both frame level pitch, as well as note level onset, offset, and pitch in this case. So this data set is something we've shared publicly and is widely available. Right. The data set we introduced in 2018 and has already been used extensively. There are only over 371 downloads and over 73 paper citations. This is the first audiovisual music multi-track music performance data set that we are aware of. That also provides ground truth for AV musical performance analysis. And we also include baseline results for typical tasks, in particular visually informed multi-pitch analysis, visually informed vibrato analysis, which I'll talk about in the following slides. Provides a very nice test bed for emerging multimedia music information retrieval tasks, including visually informed source separation, audiovisual source association, and more recently in other work that others have done, cross-modal generation. So can you generate a video of the players from the audio, or vice versa, from the video, generate the audio in this case. So I'll talk about now the several projects that we worked on this in the early stages. The first one I'll talk about is source association. This was presented at ICASP a little while back. This one I already motivated, where our objective is to, given a video performance and the corresponding audio, you like to associate each of the players with a corresponding audio track. You have an ensemble performance of Western instruments. One player is playing one part, and the parts are identified in the score, which player is playing which part, and then you would like to associate these with the individual musicians. So this is how we did this. Based on you want to do the association based on the relationship between the performer's movements that are observed in the video and the resulting tones that you see in the spectrogram, which is the signal analysis in this case. So you find the temporal correspondence between the different modalities. In particular, for string ensembles, the body motion strongly correlates with tone onset. With the finger motion for woodwind and brass ensembles correlates with tone onset, and pitch fluctuation strongly correlates with the motion done where you're changing the string. I'll highlight this as I go further in this case. So we can analyze the video to both determine where the different body parts are. This is something which modern deep learning makes relatively easy, and we've used some of that, and I'll talk about that. Then we can look at individual body parts motion, and then look at the correlation with the MIDI score, and then associate these for the different sources with the corresponding players in the audio in this case. So here's some sample from that, where you're showing this for string ensembles where the body motion is strongly correlated with this onset. We can extract body key points using deep learning techniques. In particular, open pose is one of the leading techniques in this area, which allows you to, given a video of a person, annotate key points over here. So you're seeing here the head, the neck, the point at the neck, the shoulders, and the arms annotated. So these annotations that you're seeing over here are coming from open pose analysis of the video. Once you can extract the key points of interest, you can extract the principal motions through principal component analysis to figure out what is the dominant motion of a given body part, such as the hand over here, this hand, what is the dominant motion, and then align that with this score track to figure out what is the likelihood of onset of a note being at a particular point. So here it's showing you this aligned score track. This is what we've gotten from the video, the motion speed, and from that we can predict what is the probability of onset of different notes for the players at different points. Okay. Once we have that, we can then, use that. Similarly, we can do very similar, sorry, it's jumping for some reason. Okay. So this is what we talked about for string ensembles. Similar works with the finger motion for onset for woodwind and brass ensembles. You see in this case, it's not the body motion that's going to matter, but the finger motion which is going to determine. Okay. Again, we can localize the hand and track the hand using open pose and associated trackers with that. We can then extract fine motion, and for fine motion, we actually use optical flow. Optical flow is looking at what is the velocity of movement of each pixel from one frame to the next, in this case. And this is showing you a color-encoded version of that, in this case, for two different instruments and players. Again, align with the score track and use the motion flux as an indicator of times when there are onsets of different notes, in this case. And finally, we can also do this for vibrato. Vibrato is a form of artistic expression. You will not find this annotated in the score, but this is what musicians will commonly do. In Indian music, if you're familiar with the sort of modern music traditions, they call it jugalbandi. Jugalbandi is where the musicians, as they're collaborating, will improvise and change what they're doing. So the similar kind of thing happens over here. The musicians will vary the pitch of the frequency they're playing on the instrument to make this much more expressive rather than a monotone performance of single notes in this case. This is not written in the score, but this is what musicians will do as part of their performance in this case. So this we can analyze by looking at the very fine-grained motion of the fingers. As they're playing a given note, they're moving the fingers over the strings to introduce this artistic variation, which is referred to as vibrato detection, vibrato in this case. This we can detect from the motion of the video and then correlate with the audio in this case. So you can see how deep learning enables this in a significant way, in particular by using work with others have already done in analyzing the pose of human beings in various activities, we can annotate these in a fairly efficient manner and get this information. This is showing you a correlation between the two, where you're seeing from the audio, you're seeing the pitch variation for this particular track, and from the motion of the performer fingers, fine motion of the performer's fingers, you're seeing the corresponding optical flow principal component aligning with that. And you can see these align quite well with each other. So one can be indicative of the other in this case, which is what we're going to rely on. So to evaluate this, we actually used the URMP dataset that I introduced earlier. And we expanded the dataset a little bit by using sub-combination of tracks within each piece. So within each piece, you can look at a sub-combination of tracks for analyzing, and then tested on excerpts with various durations from 5 to 30 seconds, looking at the accuracy of the association. This is just this listing of what we tested on and listing these. So how do you evaluate this? To evaluate this, we looked at the association accuracy, which is the percentage of correctly associated samples between the player and the corresponding track. So we consider an association for a testing excerpt. So if we had one excerpt, this association is considered correct if all corresponding associations are correct, meaning all the musicians are associated correctly in this case. Somebody is saying the voice is breaking. Is it fine now?
No, sir, it is fine, sir.
Okay, all right. The metric, and obviously this is a metric as the amount of data increases, as you see a longer excerpt, if you see something for 1 second versus 5 seconds versus 30 seconds, as you see more information, your accuracy is going to increase. It's also going to decrease as the polyphony number increases, which is the number of different instruments that you have. So for instance, if you were to just have a duet, 2 performers, and you were to randomly guess, this accuracy for random guessing would be half. And this goes down to, for random guessing, goes down to 1/120th for quintets, because all of the 5 factorial associations, out of all the 5 factorial associations, you need to choose the right one in order to get this correct. This is showing you the performance of the association accuracy as a function of the duration of the clip that we have looked at. For duets, you can see very quickly, after a little period of initial observation, you've gone close to 100% in this case. This is for the same thing across different instruments. For woodwind and brass ensembles, you've got woodwind and brass instruments, and across instruments which are duet, trios, quartets, and quintets. And as I mentioned already, as the polyphony, which is the number of instruments which are playing simultaneously, increases as you go down this chart, the accuracy decreases because you've got more sources of confusion. But once you observe for a longer duration of like 30 seconds, you've got extremely good accuracy in the source association. This is the same thing for mixed ensembles, not just woodwind and brass. And this shows a similar trend. You can see that when the instruments are similar, you have greater chance of confusion between them because of the audio tracks. Whereas when the instruments are different, you start off with a higher initial starting point in this case. What else can you do with this? Okay, so you're interested in a variety of music analysis tasks. You're trying to analyze what is the pitch of the different instruments. And in analyzing this, you can also use the video information. So here's an example of video-informed multi-pitch analysis. So pitch is the sort of dominant frequency of the instrument. This is visible in the spectrogram usually. So this is showing you the original spectrogram. What you'd like to figure out is what are the pitches that are there at a given point in time. And then this is called multi-pitch estimation because you've got multiple instruments playing and you have the individual pitches that are shown over here. So at each point in time, the bars over here are showing the pitches of the different instruments. You can appreciate that there are not only these bars over here that you see in the spectrogram, but also a variety of other points. Those correspond to harmonics. If you've done your Fourier series, in your Fourier series, not only do you get the component for the particular period that you're looking at for your signal, but also all multiples of that frequency. So that's what you're seeing, these other components over here. But these are the pitches associated with these instruments. Okay. In addition to this multi-pitch estimation, you're also interested in how this progress over time. So which of these correspond to a single instrument and single player across time? That is referred to as multi-pitch streaming. That is annotated in the color you see over here. So the blue pitches correspond to a single instrument and player. Similarly, the cyan pitches and red pitches correspond to a single pitch and player in this case. Okay. So multi-pitch estimation estimates instantaneous pitches and polyphony, how many players are there, and what are their respective pitches. Multi-pitch streaming organizes these pitches into streams corresponding to individual sources in this case. So very simple technique that we used was we detected in the video which player is playing and which player is not playing, and use that to provide instantaneous polyphony number, which then assigns only the detected pitches to active sources. So we can use this. In the video, we can analyze individual players to figure out which players are playing or not playing at a particular instant in time. This gives an estimate of the instantaneous polyphony and number of players. You can associate them with the active sources and then estimate multi-pitch in this case. Once we've done this, we can then build upon that and do the multi-pitch streaming. For the details, I'll refer you to the paper. Obviously, in the time I have, I will not be able to go into all the details that I have. So just a very quick highlight of how we detect play and non-play. As I already mentioned, we have ways of localizing the body parts based on deep learning techniques from OpenPose. Once you've localized the fingers, for instance, somebody who's playing a string instrument, you can then detect the player, detect the hand. You can do fine-grained motion analysis through optical flow, and that's encoded over here in motion features. From the motion features, you can then analyze to determine whether you would classify them as playing or not playing in a given point in time. This gives you the multi-pitch estimation accuracy that you get. So this is comparing a variety of options. If you were to do this based on audio alone, that's the dark box over here. Those are the dark whisker plots over here. And then if you do visually informed, you see you get a substantial boost in performance compared to audio-only techniques. Okay. And if this is informed by ground truth play and non-play, you've got a further improvement. So the gap between these two is caused by the inaccuracy in our play and non-play detection in this case for these different instruments. You've got a significant improvement in this case. Similar thing with multi-pitch streaming accuracy. By knowing the number of active sources, we can then estimate not only the pitch more accurately, but you can also use that to try and use along with the source association to figure out what is the streaming and improve the streaming accuracy in this case. And you can see this. In this case, you can see the gap between what is informed by ground truth for play non-play and what we've got is not that large. The problem is more challenging for quartets than for duets, which is what you can also imagine. If you have only two players, you can do the better job with this. But as you go to quartets, the improvement is much smaller and the task is more challenging. The final sort of project I'll talk about is something which has not been previously investigated because there were not really easy tools for doing this. This is video-based vibrato analysis. So I already mentioned, so this is the phenomenon of vibrato. So I'll try and play the audio here. I'm not sure what's going on. Okay. I guess I should debug the, oh, sorry, maybe I don't have the file here. My apologies. Oh. It's not giving me the option of doing anything else other than. So I will have to probably close this. It probably did not link the audio file. My apologies for that. So let me restart the program. My apologies. I think I should have tested the audio better earlier. So yeah, these are two recordings. One is without the vibrato effect, and the second is with the vibrato effect. So without the vibrato effect, you've got this rather flat spectrogram where the instrument pitch is not being varied. So you don't see any variations in this frequency spectrogram. And with the vibrato, you can see that these variations are being introduced. And this is a form of artistic expression, which is considered quite important in performances. This is something which the artist is doing. The note is only informing them what this corresponds to, but the artist themselves is introducing this variation by moving these fingers in this fairly fine-grained motion to modulate the pitch. Okay, you're modulating the pitch of the note in a periodic fashion in this case. Okay. So this is characterized both by the rate, which is what is the rate at which this is occurring, what is the frequency at which this is occurring, and the extent, which is the duration over which this vibrato effect exists. So my apologies, but the audio sample here would have illustrated the two and the difference between the two. This would have sounded relatively flat. This would have sounded like it has some variation in it, which is introduced by the artist in this case. Okay. So how can video information help improve analysis of the vibrato? This is showing you our overall scheme. We have the audio, we have the MIDI score. We can align the score to the audio. From the MIDI, we can associate, from the video, we can associate the tracks with individual players, extract motion features for the tracks, and then detect vibrato in the video, and then analyze the extent of vibrato and the rate of vibrato from this extracted information. So I'll highlight this a little bit more in detail. Next slide. This is showing you the ground truth. As I mentioned, we have individual tracks. So in the individual tracks, we can annotate the pitch, and we can also see the variation in the pitch that you see over here. For something which is, if you're doing this audio-based alone, if there is something which has got multiple instruments, this task becomes much more challenging. Okay. So you try and have the spectrogram, and from that estimate the pitch, you can see that this is performing much worse than this. However, if you on the video, you've associated this track with the particular performer, you've got the localization of the hand to the analysis of the pose using deep learning techniques. You can then analyze the motion of the fingers, this modulation that they're doing with the fingers of the notes, and use the hand displacement and analyze that. And you can see that there's a very strong similarity between the signal you see over here and the signal that you see over here. Okay. So for vibrato detection, we do hand tracking. We track the hand. We track specific key points also in the hand using a Cardinal Loewe KLT tracker. And then we also do optical flow estimation to estimate the predominant motion in this case. Once we've got this, we can then take each note segment as a sample and use a classifier. In particular, we use a support vector machine classifier to classify between vibrato and non-vibrato for a given note segment. Now, once you have that, you can then further analyze the vibrato in terms of the vibrato motion rate as well as the extent. So what is the idea behind motion rate? So the variation in frequency that we talked about, which is the basic aspect of vibrato, is caused by the finger motions modulating the pitch. So the two are going to be at the same rate. The rate at which you're moving your fingers is going to be the same rate at which the pitch variations are going to be introduced. That's what you see over here. Okay. So you can figure out the vibrato rate from the motion rate. Analyzing the audio itself is more challenging in the presence of polyphony, but because in the video you've separated this to a particular source, you do this much better in this case. Okay. So we do principal component analysis of the motion vectors from the optical flow, and then the vibrato rate is directly the motion rate. Okay. The vibrato extent is not that quite direct. The extent of vibrato is normally characterized in terms of this unit called cents, which is looking at you can think of this as the percentage of variation in the frequency. I'll give the more exact definition later. So that's not exactly matched between the two, but you can scale this according to the motion extent, scale it according to the pitch contour, and obtain the vibrato extent from that. So how does this perform? This is characterizing the vibrato detection and if you compare this if you do this based on audio alone techniques, the two audio techniques that we tried, the accuracy is fairly low in the presence of polyphony because there are multiple instruments. Whereas when you can do this in video, the accuracy is quite high because you've got a source of information which is quite disentangled from the different. So you significantly outperform audio-based baseline systems. Vibrato rate error is fairly small, as you can see. This is showing you a whisker plot of the vibrato rate error over here. It's about 0.38 hertz across this many vibrato notes. And the extent error is 3.47 cents. Cent is a relative unit in terms of in the frequency domain. I will not go into the details of that because I'm already a little bit short of time.
Yes, sir. Sorry to interrupt, but we have to find a bit.
Yes. So that's, but that was my final slide in terms of the technical content. So to conclude, music is inherently a multimodal art form, and increasingly distributed as multimodal video. This creates new opportunities for signal processing and also for machine learning, which if you combine multimedia signal processing along with modern machine learning techniques, this provides a particularly powerful way for analyzing music to solve both new problems as well as get new solutions to old problems. The problems I illustrated through in my examples sort of show how this power can be harnessed. I talked particularly about a few different problems: source association, associating the player with the corresponding track, multi-pitch estimation, estimating the pitches of multiple instruments playing together, and their progression over time, which is the streaming, and vibrato analysis. And in these problems, joint audio-video analysis provides significant improvements over audio analytics alone. This is a new area, and obviously we've only just scratched the surface. There are many opportunities for additional research in this area. And as I already mentioned, a lot of people are also using the data set we created for their research. It's being extensively utilized. So thank you. I'll be glad to take questions that people may have.
Thank you very much, sir, for insightful presentation. There is a quick question from Khadija. She is asking that what do you mean by multimodal data?
By multimodal data, I mean what I showed you in this case. So if you look at the data we have not only the audio recording, we have the audio recording for the music performance. We also have the video of the music's performing. We also have the score. So that's an example of multimodal data. You've got the same signal, same underlying, what you would call the music composition, same underlying music composition represented in different modalities, represented in audio, which you've recorded, which is shown in the spectrogram over here, recorded in video, and available in the score.
And sir, what is the multi-track and the multi-channel? Both are the same or the different?
So the multi-track is typically referring to the tracks in the score. Multi-channel is referring to the audio. So they are really, in my opinion, the same, but referring to different modalities. The multi-track is normally used for audio, and the multi-track is used for the scores over here. So they are essentially the same thing.
Okay, and did you also perform cross-model analysis in your work?
So when we're doing the analysis of the multiple modalities, in some sense, it is working across the different modalities. So when you're doing joint analysis, you're actually also incorporating cross-analysis. So for instance, when we looked at the vibrato, we figured out the extent of, we figured out the vibrato rate from the motion. So that is really cross-modal analysis. We are figuring out what is the rate of vibrato from the, so the rate of vibrato that we are looking at over here, we're estimating from the video modality. So even though we're interested in this rate, We do not have this clean signal by itself because the signal is mixed with others. We cannot do as good a job with this, but by analyzing this other modality, we can do a much better job. So that's an example of cross-modal analysis.
Okay, sir. Okay, thank you very much, sir, for insightful presentation. And it will really open new dimension, and it will be really a new beginning for something new research area that can be done. And on behalf of entire team, I am thankful to you for your presentation. And I want to share the e-memento. So Tejal ma'am, please share the e-memento.
Thank you.
Thank you very much, sir.
you.
Sir, I have one question that last question I got, and I think that I have to ask you this question.
Sure.
Can you suggest any Indian language speech data set? It is interesting question.
I think
Maybe not
there-
related to it.
So can I suggest Indian language speech data set? I have not looked at data sets recently. I know there is a lot of work on Indian language speech recognition and techniques specialized to Indian languages. In particular, the Indian Statistical Institute has been working on this problem for a number of years. So there are conferences that I've been to where there have been presenters from ISI in Calcutta, where they have presented their techniques for Indian languages. So I would suggest you look at those as a source of data. And I'm not sure if they've made the data publicly available or whether that's something available only upon request. So I'm not directly aware of, I've not worked in that field myself recently, so I've not looked at it. But two suggestions would be, one is to first search on Google and also on dataset repositories such as Dryad, which is where we publish the data, IEEE Dataport, which is also increasingly published a lot of data sets. And if you don't find these there, then I would suggest trying to look at the researchers from ISI who've been working on Indian languages and looking at their publications and contacting them to see whether they've made they can make the data available publicly.
Great, sir. Tomorrow we have one speaker, Professor Ashish Ghosh. He is basically from ISI Kolkata.
Okay.
He may able to give justice about this question.
Yes.
So thank you, sir. Now I want to say that we have the quiz link enabled, so you can take the quiz, as well as the form is also available. So you can fill that feedback form. Quiz will be enabled only till that next speaker will start the session. So it will take you have just time up to 3 to 4 minutes.
Okay.
So now over to you, Nita madam.
Thank you, Chirag sir. May I audible?
Yeah, but before that, can we have one group photo? We have both the speakers with us. We have Dr. Achin Bhomik sir and Gaurav Sharma sir, both are with us. So we can have one group photo. So Tejal ma'am, can we have one group photo?
Yes, sir.
Please turn on the videos, all the participants. तेजल मैम स्माइल करने को बोलना. You smile.
Yes, one more smile, please. Thank you, everyone.
Thank you. Thank you.
Thank you. Nita ma'am, over to you.
Yes, thank you. Now today we have the third session. Sir, should I start? We have to give time to the participants to complete the.
No, ma'am. Just you can start introduction about speaker.
Okay. 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 Okay, good evening everyone in India and also good morning outside the India because there may be the morning somewhere and evening somewhere. So good morning and good evening to all. Today in the third session, we have Dr. Achin Bhaumik and I would like to give his biodata. Actually, I have a limited time, so I will try my best to include a majority of the things. So the Dr. Achin Bhaumik is the Chief Technology Officer and Executive Vice President of Engineering at the Startkey Hearing Technologies, a private held medical device company with over 5,000 employees and operations in over 100 countries worldwide. Previously, he was Vice President and General Manager of the Perceptual Computing Group at Intel Corporation. He also serves on the faculty of the Stanford University as an adjunct professor at the Stanford School of Medicine, where he advises the research and lectures in the area of cognitive neuroscience, sensory augmentation, computational perception, and intelligent systems. He has also adjunct and guest professor position at the University of California, Berkeley Liquid Crystal Institute of the Kent State University, Kyung Hee University, Seoul, and the Indian Institute of Technology, Gandhinagar. Dr. Achin is a member of the Board of Trustees for the National Captioning Institute, Board of Director for the OpenCV, Board of Advisors for the Funk Institute for Engineering Leadership at the University of the California, Berkeley, and Industry Advisory Board for the Institute for Engineering and Medicine and Biomedical Engineering at the University of the Minnesota. His awards and honors include Fellow of the Institute of Electrical and Electronics Engineering, Fellow and President-elect of the Society for Information Display, Healthcare Heroes Award from the Business Journal Industrial Distinguished Leader Award from the Asia Pacific Signal and Information Processing Association, IEEE Distinguished Industry Speaker, Times-Based Inventions, Red Dot Design Award, and the Artificial Intelligence Breakthrough Award. He has authored over 200 publications, including 2 books and over 80 granted patents. Dr. Bhaumik and his work have been covered in numerous press articles, including Time, Fortune, Wired, USA Today, US News and World Report, CBS News, BBC, Forbes, and many more. So now coming to the topic, like we heartily welcome you, sir, for giving your time and giving us the opportunity to hear you, to grab the knowledge from you. So we heartily invite you for the session 3. Now the topic for this session is on augmenting human sensory perception with artificial intelligence. So without wasting much of your time, sir, I will give mic to you. Thank you, sir.
Anita, can everybody hear me all right?
Yes, sir.
Okay, sorry, I should have sent you a shorter version of my bio. Took a while to read. So I'm going to share. Looks like the share button is not allowing me to share my screen here. Can you give me permission?
Just wait, sir. Tejal ma'am, can you just do the?
Yeah. Now I see I can. So please let me know when you are able to see my screen.
Sir, it's visible.
And I'm going to go full screen. Hopefully it will still be. Are you seeing the full
Yes,
screen?
sir. Yes, sir.
Okay, so first I should say thank you for inviting me. I did get up pretty early in the morning to see everybody. I wish this was in the good old days, face-to-face, in-person meeting, but we'll do the best we can in the online format. If anybody has in the middle of the presentation, you can't hear me or cannot see a content, please stop me so I don't keep going if there is a problem with technical setup. Is that all right, Nitu? Okay, so
Yeah.
with that, let me get started. So I designed this to be sort of kind of a blend between a bit of neuroscience and a bit of engineering. There are three questions that we're going to ponder about at a high level. How do we sense and understand the world? So we're going to touch upon sensory perception. That's the neuroscience or biology part. And then I'll briefly go over sensory deficiencies. As amazing as our hearing and vision are, which is what I'm going to primarily focus on, there are problems that we encounter as we get older or as we subject ourselves to unhealthy levels of stimulus. The reason I'm going to focus on only hearing and vision, mostly hearing if time runs out, is because we just don't have the time to cover all of the other amazing senses like smell, taste, somatosensation. And then finally, the topic here, how do we use the modern machine learning algorithms and sensors to not only enhance human senses such as hearing and vision, but how can we augment them to get to what I call superhuman sensory capabilities. Chirag, is that good enough for content? I will do my
Yes,
best
sir.
to make it interactive.
Yes, sir, you can.
All right. Okay, so human sensory perception certainly is amazing. The fact that we can simply open our eyes and make sense of the world is phenomenal, because all that's happening is your sensors that are embedded in the body transducing the energy from environment and producing neural pulses that are being processed in the cerebral cortex. That's pretty amazing. It's a cacophony of signals coming from all around the world. The photons entering your eyes, getting transduced into neural pulses that are getting initially processed in the visual cortex. The hearing, which I'm going to talk a lot about, the sound signals getting converted into neural pulses, which are first going to the auditory cortex, and then somatosensation, the touch signals coming to the somatosensory cortex, etc., smell and taste. And then we are effortlessly creating a model of the world and constantly updating that model. That is allowing us to take actions. And then along the way, we are learning every moment. New data is coming in, and the model of the world in our head is getting updated. So we're learning along the way. So this is pretty phenomenal system that you have. The brain consumes less than 20 watts. So it's pretty amazing how it does all of that work in a short time. But before we leave that, for us engineers and neuroscientists, the human sensory perception system is really just a window to the reality. It is not a measurement system. I skipped a lot of slides where you could actually design experiments to fool your sensory perception system to show it. These sensors we have and the processor, it's not designed to be accurate measurement of the stimulus in the environment, but it really is designed or evolved to create and update our model of the world. So it's really our window to what we call the reality. Okay, with that, let me quickly go over. So what are the problems that we encounter, which is what forms the basis of this field, not only in academic research, but also billions of dollars of industry. It's an important part of human health. And I'm going to give you a few examples, not a comprehensive list, but according to World Health Organization, WHO, about 500 million people, that's almost 500 million people. The last count was in 2016 and it was 466 million. So nearly 500 million people live with disabling hearing loss worldwide. So what is disabling hearing loss according to World Health Organization? When we have so much hearing loss that the sound that's coming into your ear has to be amplified by 40 decibels. So that's a log scale. That's a 40 decibel is 100 times increase or amplification in sound pressure level. So that's 10,000 times amplification in the sound energy. So think about it. These people who WHO calls are living with disabling hearing loss, for them to be able to hear the world, understand your conversation, the sound energy has to be amplified by a factor of 10,000 for them to just barely hear it. This is a big health crisis. And more important, by 2050, the projection is that this number is going to double. That's because the older population pool is growing quickly, and the problem is getting worse. We're subjecting ourselves to loud music and sound from the cityscape, etc. All right, and then other sensory problems. Approximately 40% of the population experience balance difficulty, particularly as you get older. The degradation in the vestibular sensory system results in problems in our gait and fall injuries. A lot of older people will fall and hurt themselves as they get older. In the US alone, the statistics is it's costing the US economy almost $70 billion every year. Next, vision. I think this is what is understood very quickly because many of you and us wear glasses, right? So despite that, according to WHO and NIDCD, at least 1 billion people are living with vision impairment that are yet to be addressed. And those are not just the refractive errors, the problems in the lens, but also macular degeneration, diabetic retinopathy, etc. And there is 20 to 30 million legally blind people, right? So this is a very significant problem for humanity as well. Before I leave this, just so you know, the smell and taste are important subjects as well. I got the US data. 13 million people have smell dysfunction, also called, many of them have anosmia, which have no sense of smell. And many people among those 13 also have severe hyposmia, a minimal sense of smell. When you lose the sense of smell, this is not just a social problem. Actually, it's a major risk. If you can't smell odor in the environment, you might inhale dangerous levels of polluted air or chemicals, and that causes health problems. And almost 19% of Americans, again, worldwide probably similar number, suffer from ageusia, which is a degradation of sense of taste. So you can't really tell. With COVID pandemic, I think it became clear in the early days of COVID, loss of smell and taste were cardinal symptoms of COVID as well. So this we become more aware of it. All right, so with that, I'm going to dive into the world of hearing. And as I said, I'll start with taking a little bit of a deeper look into how we hear, what happens when you don't hear, and then how do you use artificial intelligence to help people hear better. And I think this is, here I'm going to test myself as well to see if you can hear my audio, or do I need to do anything on the setup. So first thing I ask, and I hope somebody is going to volunteer, do you hear me?
Yes, sir.
Okay, so now let me tell you, the fact that you can hear me is a miracle. It's magical. Just think about what's happening here. I am just, my vocal tract, which really the generation of sound, right? It starts in my lungs. So the lungs creating the pressure, which is forcing air column to essentially create a pattern of vibrations that are traveling through my vocal tract and come out of my mouth. All I'm doing is just pushing air molecules. And those vibrations of air molecules propagating out of my mouth, being picked up by the microphone here, getting converted into electrical signal. On your side, I don't know what speaker you're using, which is in turn getting the signal and pushing the air molecules. And then you are receiving the vibrations of air molecules with the eardrum. And your brain is making sense of it. So the fact that you can understand what I'm talking about is a miracle. So when I present on sound, I like to play some sound. And let me know if you can hear it. Are you hearing on your side?
Sir, again you play
Okay.
and keep volume higher.
Are you hearing, or do I need to do
Yes,
something with my audio?
a
You are
little
hearing?
voice is coming.
Okay. So what did you hear? What kind of sound did you hear?
Again play, sir. It's
Yeah.
like a noise only.
Okay. Yeah, it is noise. So what you hear is like almost like a background sound in a restaurant. Okay, let me play this one on the right.
Happy birthday to you. Happy birthday to you.
Happy birthday. It's hearing.
Okay, so now you could tell the difference between the two. One was just a background sound in a restaurant, another was a song. But what's interesting is that the effect on your ear was simply that your eardrums were vibrating back and forth. That's all. And so your ears are receiving simply pressure waveforms that are going up and down as a function of increasing pressure and decreasing pressure in the air that's inside behind your eardrum, and the pattern is shown on the right: pressure versus time. So it's fascinating that we can make sense of just simply this pressure wave that encodes all of the information about the sound. And the goal of our auditory system is essentially to interpret what's going on out there, and that allows us to take actions. So it's not just the ear, but it's the entire chain of actions processing from the ear itself, and then the brainstem, the midbrain, the thalamus, and auditory cortex. So we don't hear with our ear, but with our entire auditory system. So for those of you engineers amongst you, I need to calibrate you on some numbers. This is a complex chart, but I'm going to get over in a couple of minutes. The x-axis here are the frequencies. So you've heard things like human hearing ranges from 20 hertz to 20 kilohertz. That's the sound wave you can hear. Ideally, as we get older, we don't hear the higher frequencies that well. And of course, you might have heard cats and dogs can hear even higher frequencies. Elephants can hear lower than 20 hertz. On the y-axis is the decibels in sound pressure level, which is defined on the right. So decibel is 20 times log of P over P0. P0 is the reference pressure. It's taken to be 20 micropascal. So just think about it. The atmospheric pressure, where you're sitting right now, sea level, is about 101 kilopascal. And 20 micropascal is the level of signal that we can barely hear at 1 kilohertz level. So at 1 kilohertz frequency, not level, 1 kilohertz frequency, we can hear 20 micropascals. That's less than 1 billionth of the variation in the atmospheric pressure level. And so as you can see, at lower frequencies, the pressure needs to be a little higher for you to hear. And we are very sensitive in the range between 1 kilohertz to about 6 kilohertz. That's where the human speech frequencies happen to be. And that's the center island that you see here in the light green. When we speak, we are producing sound in the frequency levels of 300 to 500 hertz to about 4 to 5 kilohertz. And we're creating sound pressure levels between about 35 decibels to about 65 decibels. And then pay attention to the top curve, the loudest levels of sound that you can tolerate. That's about 120 decibels. So the dynamic range of hearing for humans is pretty amazing. It's or 12 orders of magnitude in terms of energy. So with that, let's take a look at the ear itself. Very, very quick journey into your biology class. When you say ear, it's got three sections: the outer ear, which consists of your ear flap and the ear canal; the middle ear, which consists of the three smallest bones in our body; and then the inner ear, which is where the signal transduction happens. Sensory system is in there. We're going to take a look at that. In fact, when you say, where is your ear? We tend to say, this is my ear. That's the least important part of our ear. The ear flap does work like, you can loosely call it an acoustic antenna. It helps guide the sound signal into the ear canal. It also, because of its shape, it has frequency shapings, frequency filtering characteristics, which help us with directionality, but not much else. The ear canal has a resonance frequency amazingly in the same range where we speak. So actually, the combination of the ear flap and the ear canal can amplify the mid-range of frequencies, which is where our speech frequencies are, by as much as 10 to 15 decibels. And then your eardrum, and I'm showing 1/3 of that here, cut out portion, vibrates back and forth in response to the sound pressure levels going back and forth. That sets in motion these three bones to go back and forth, and they actually work together to amplify the sound further by as much as 27.5 decibels, big amplification. But then magic happens in the cochlea. So I'm going to show you a cross-section of this spiral-shaped cochlea in the next slide. And I'm going to go fairly quickly here. If you take a cross-section of the cochlea and blow it up on the right here, this is where it's called organocorty, where the transduction of sound happens into neural pulses. Pay attention to this row of cells, which are called inner hair cells. So as the membrane on the top is touching the tip of the sensory cells, as it goes back and forth, because of a traveling wave pattern created by the sound that enters the ear, it wiggles the tip of the hair cells left and right. That's because the basilar membrane, the membrane at the bottom, is going up and down because of the traveling wave. And that essentially creates ion channels to open up. It causes the ion channels to open up, and the hair cells release neurotransmitters, which are then picked up. The signals are picked up by the auditory nerve fiber, which are sent to the auditory cortex. That's essentially the transduction of sound. And I'm going to talk about this other three layers of hair cells, which are called outer hair cells, in the next couple of slides. So this mechanism was first discovered by Professor Bekesi, and for this work, Dr. Bekesi got a Nobel Prize. And he actually worked on human cadavers to show how if you take the cochlea, it's at 2.5 turns, but how different parts of the cochlea was responsive to different frequencies, such that the cochlea was working as a frequency analyzer. So for this work, he got the Nobel Prize, and he demonstrated through measurements on human cadavers, different parts of the cochlea vibrating to different frequencies. I'm going to show you a quick illustration here. So as you can see, higher frequencies of sound will make the base of the cochlea oscillate, and lower frequencies of sound will make the tip of the cochlea resonate. And then subsequently, a lot of experiments have been done. And this is a data from CAT frequency tuning curve. So as you can see, as you literally insert electrodes into the auditory nerve fibers along the cochlea, different parts of the cochlea are tuned to different frequencies. So the sharpness, though, required us to update the Bekesi model, because the model that Bekesi had that tried to explain the frequency tuning with the patterns of vibrations of the basilar membrane did not quite explain the sharpness. So this model was updated with the model of an active amplification that happens in the inner ear. I already told you about amplification that happens via the ear canal, the 3 middle ear bones, and the final levels of amplification, in fact, the largest amount of amplification, as much as 50 decibel, happens through the actions of the outer hair cells, which consist of a special type of molecule, protein molecule called prestin. So in response to sound waves, the prestin molecules elongate and contract, mechanically amplifying the sound by 50 decibels before they get converted into neural pulses by the inner hair cells. So that's what's pretty amazing. I would encourage you to pick up a chapter book on human ear, and you will never hear the same way again, because you'll develop a different levels of appreciation for how your hearing works. So I'm going to now switch gear to hearing loss. Before I talk about what we do with AI to help people with hearing loss. What I'm showing you here is called an audiogram. So if you have hearing loss and you go to an audiologist, they're going to measure your loss of sensitivity by placing you inside a sound chamber and playing sound in your ear at pure tone frequencies. And they will establish what level of loss you have in your sensitivity for each of those frequencies. And then they'll create a curve like this that you see on the right. So this is a typical example of an age-related sensory neural hearing loss. Just think about, so the x-axis frequency, y-axis is the hearing loss level. So if you are in the 0 to 20 decibels, it's relative to the normal hearing, then you're considered to be normal hearing. If the sound has to be amplified up to 20 decibels for you to barely hear, that's perfectly all right. But if you have mild hearing loss, the sound level has to be amplified by up to 40 decibels for you to hear. Moderate hearing loss between 40 to 70 decibels, and severe hearing loss between 70 to 90, anything above 90 decibels called profound hearing loss. So I'm going to come back to this chart, but before I do that, let's take just one final look at what is called the speech banana. It's a fun way of explaining qualitatively and quantitatively what are key characteristics of speech, because while the sense of hearing is for hearing the world, one of its primary function is to help understand conversation, speech, talk to each other. So if you look at this diagram here, the left side of it are all the vowels, A, E, I, O, U. These are the basically low frequency patterns we create in the air molecule vibration as we speak. I was talking about how air column is pushed out through our vocal tract, shaped by our passage through the nose and the mouth. The tongue participates in shaping the acoustic signals. So the lower parts are all of that mostly contains energies. As you can see, those are high levels of energy, up to 60 decibels. And then the shaping of it, when you say F, TH, thirsty, first, which are the shapings that happen with your lips, those are at higher frequencies, because you're letting the low frequency energy go out, and on the way out, they're getting shaped by your lips. So we can't say, for example, P without closing our lips, right? How about D? You can say D without closing the lips, but in order to say P or B, you have to close your lips. So those frequency shapings that are responsible for fricative transitions happen at very high frequencies, between 4 and 5 kilohertz. And they also tend to be lower energy, 20 to 35 decibels. Now, let me go back to the chart that I just showed you. This patient whose audiogram I'm showing you, look at 4 to 5 kilohertz, which is where your consonants are, and they're 20 to 30 decibels, maybe 40 decibels at 4 to 5 kilohertz. So go back and look at 4 to 5 kilohertz here. You can see this person needs the sound levels to be 60 to 70 decibels for them to hear those consonants. Whereas when you normally speak, we only produce maybe 30, 40 decibels. So this person will not be able to understand conversation. They'll be able to hear your loud sounds fine, like the vowels, but they won't be able to distinguish between P and B and D, and they won't understand conversation. That's what happens when you lose speech. Now, I do have a simulated audio that gives a sense of what is it like to live with hearing loss. I hope you can hear it. Let me see if you can hear it. This is the music created by the Ear Science Institute in Australia, and it simulates hearing loss. So it's going to play normal sound, and then it's going to play simulated sound for someone who's got different levels of hearing loss, mild, moderate, severe. Let me see if you can hear it.
I know I'm young, could be a little bit wiser, but there's shadow love, and I think enough of haze and fire and eyes to know the call.
Can you hear the song?
Yes, sir.
Okay. So back to normal hearing. It's going to simulate different levels of hearing loss.
For once in your life.
Okay, I'm going to pause right there. Profound hearing loss is something where you cannot hear anything. So now you should get a sense of what is it for the 500 million people that are living with hearing loss, because they can't hear. So be patient with people when they say they have hearing loss.
I know what.
So let me move forward. And this is Helen Keller, the famous Helen Keller, who was both blind and deaf. And she said, blindness cuts us off from things, but deafness cuts us off from people because you cannot hear them. And she, as I said, she was both blind and deaf, so she would know. So now I'm going to get into technology. And so what can you do about this problem? How can you bring technology? More important, how can we use modern techniques like AI to make better hearing technology? So let me start with a little quiz. I know you guys have quizzes there. So anybody knows who this gentleman is? That's my first quiz question. Any guess? Anyone? So this is Beethoven. You're still hearing me, right?
Yes, sir.
Okay. So Beethoven, he died in 1827. The legend has it that he lost his hearing, and towards the end of his life, he had lost such sense of hearing that he had to turn back after finishing a performance to see people clap because he could not hear them clap. So anyway, so here you see him using an ear trumpet to amplify sound. It's essentially bringing in sound signal through a big opening and then it's narrowing into a funnel. So it's basically just using a mechanical amplification to hear better. So that was the hearing aid in the late 1700s to early 1800s. Okay, so I need to get back into the screen here. Okay, and then in the mid 1900s to late 1900s, you would get hearing aids like this. There'll be body-worn devices that would clip on your shirt or pant, and then the electrical signal will be sent to an in-ear device. And those were the hearing aids of late 1900s. In the early 2000s, hearing aids got smaller. You had digital signal processors, micro electromechanical systems, MEMS, sensors. But the devices were still ugly looking. If you look at this 2009 BBC article, they wrote how people were ashamed to wear hearing aids because these devices were not really good looking. They were big and ugly. So there was an opportunity to transform hearing aids. So we did some work here. I'm going to talk about this. Can we use modern technology to do three things? One is make better devices, make them really good designs, and use AI to help people hear the sounds that they care about and suppress the sound that they do not care about. Can we use machine learning techniques, extremely low power, lightweight machine learning techniques to classify the sound and choose to amplify only those that matter? And then the second part you see in the middle, can we embed sensors and use machine learning on the sensor data to also turn these devices into your health tracking devices? Last but not the least, can you connect this hearing aid to the cloud to become gateway to the world of information and become your personal assistant? So you can ask anything and get an answer spoken into your ear. So let's first take a look at the first thing, which is design. What I'm showing you here on the screen are the hearing aids we made. We sold millions of them, making more than $1 billion in revenues from it. These are designed to be ergonomic and discreet, comfortable. In fact, it may not be fair because it's difficult for you to see me on a small, on the screen. But did you notice I'm actually wearing these devices? Anyone has noticed? I can challenge you because even when I'm in the room, you won't notice it until I take it out like this and show you. This is the same device that I'm showing on the screen. So these are designed to be discreet, modern looking. You can really see them even with a close look. And I don't have any hearing loss, yet I use these devices because they're also my Bluetooth headset that are streaming audio from phone. And when I'm in a business meeting, I will tell you, because of the AI that we have in here, it can provide signal to noise ratio enhancement of several decibels for conversation versus restaurant noise. I'm going to talk more about that. And then there's different form factors that these devices come in. Let me switch gear to AI and to give you some sense of what have we done or can be done to give you superhuman hearing, better than your normal hearing. Not just help people hear better who have lost the sense of hearing, but even for people like me who do not have hearing loss. Why do I still use these devices? Well, so diving briefly into the technology here, the work that we've done along with many other laboratories around the world, including academia and industry. I'm actually borrowed this diagram from the work of Professor Josh from MIT, sorry. So on the left, you see a model of the human hearing, the model of the cochlea to the midbrain. So essentially sound waves come in and we model it after the cochlear filters to filter them with a series of filter banks, essentially. A continuous set of 24 filter banks that we have in the hearing aids that split the channels into different bands of frequency. And then you model the outer hair cells that I told you about that provides a nonlinear amplification. You amplify the lower levels of sounds a lot more than you amplify the higher levels of sound. So you provide a non-linear amplification modeling after what happens in your healthy outer hair cells. Unfortunately, when people get older, those outer hair cells degrade and they lose their non-linear amplification functions. So the hearing aids have to provide that capability. And then as you get into the higher levels of get out of the cochlea and get into midbrain and thalamus, you have other filter banks that basically they create the envelopes of undulations of the sound waves, sound energy in lower frequencies. So we have to model that. And finally, as I said, you understand the conversation in your head, not in your ear. Ear is simply sending signals into the brain. And we're doing some work now on clarifying speech versus noise with deep neural network techniques, such that not only the hearing aids amplify the frequencies that are needed by the amounts that is needed for a particular patient, compensate for losses in the biological outer hair cells, but also advanced signal processing with deep neural nets to help people understand speech better in noisy environment. So I'm going to show you a demo from my lab. We are using deep neural network to see if you can clarify speech signal in loud and noisy restaurant. So I'm going to play this demo, and initially you're going to hear noisy background and somebody's trying to talk. That's what typical restaurant or cafeteria environment is. The second half, we're going to send the signal through a deep neural network to enhance speech and suppress noise through the hearing devices. Let me see if you can hear the difference.
Straight in that direction, and the arrow is red, and I'm just staring at it for a moment thinking, this is really strange. For a good 2 or 3 seconds, I'm seeing cars, 2, 3.
So hopefully you heard the first half was really noisy. You couldn't understand anything. And after processing through a deep neural network, the speech becomes comprehensible and the background is suppressed. So that's what I mean by superhuman hearing, because even your normal healthy hearing system doesn't have this capability. But with technology, with advanced hearing aids, with deep learning technique, we can help us hear speech in such a loud and noisy environment where even our normal biological hearing fails. That's the power of these modern techniques. And of course, we can go beyond sound amplification. The devices that I just showed you, they're able to track your physical activity because we have sensors built in, MEMS sensors. They can measure a patient's social engagement. As if I buy my hearing aids for my old grandaunt, we know being socially engaged is good for health, and being lonely, not interacting with people, is a sign of early onset of social withdrawal, which leads to degradation of your cognitive abilities. And that's really bad, right? It's signs of dementia and Alzheimer's and all of the bad things that happen. So these sensors can detect the level of social engagement that's going on through machine learning analysis of sound that are being collected by multiple microphones in these devices. And it also comes in with a built-in personal assistant because we have a Bluetooth radio in these devices. In these tiny devices, you've got Bluetooth radios that connect you with the world of information. You can ask anything. You just double tap my hearing aids and I can ask what's the weather, and it will tell me in my ear. It can translate 27 languages. So you could translate between Hindi and English or any other 27 languages. You can look at our website to see what are those languages we can translate from. And the other things that we've been able to do is train an AI model to be a very accurate classifier for fall. So if the patient wearing these devices fall, the sensors in the device can automatically distinguish between various different physical activities: walk, run, sit, stand, lie down, and fall. If he fell, we've been able to collect a lot of data to develop a highly accurate fall detector. And once the fall is detected, the device sends signal to the caregivers that you designate. So if somebody in the US and Europe, where many older people tend to live by themselves, and we get a lot of feedback how this automatic fall detection in the hearing aids are saving people's lives, because we have an example of an 85-year-old gentleman falling in the state of Alabama, and his son getting an alert message in another state, and he called up the local police station to send help. Otherwise, his father would have passed away. So this is really a life-saving technology now. So besides amplifying sound, it's also helping people live safer lives. We got, so I'm going to brag a little bit. Bloomberg Businessweek wrote this article after talking with us, that the future of wearable technology is called a hearing aid. Because even if your ears are fine, this is a snapshot of that article, you might want a device that translates languages, tracks fitness, monitors vital signs. We got the Time Best Inventions Award in 2019. I'm also proud that in 2020, we got the AI Breakthrough Award and the Consumer Electronics Show Innovation Award in 2021, and a number of other awards. For those of you that would like to learn more about it and dive into the details, we just published end of last year a pretty comprehensive article on IEEE Computer Magazine. Send me an email and I can share the PDF with you, or you can look up, Google search it. So with that, I got 5 minutes or so. First, I want to see if you have questions on anything to do with hearing before I spend a few minutes on vision. Because if I run out of time, yeah, sorry, go on.
Yeah. The question is that regarding that fall event, like how they are identifying when the person is directly going for the sleeping, or it is some injury due to that it is falling.
Yep, thank you for asking that question. So this is where the magic of artificial intelligence and machine learning comes in. Because for many years, our engineers, as well as researchers in other academic labs, try to develop handcrafted signal processing algorithms to detect fall and separate it from other natural motions, like gently lying down, or even lying down on the bed or moving your head. It's a very difficult problem. Much like we all know about the decades of attempt to develop computer vision technique for object recognition with classic signal processing and image recognition algorithms. But the problem was solved when you had lots of data and machine learning techniques trained with the data. So in short, we've collected lots and lots of data from people sitting, walking, falling, lying down. And then we trained machine learning models with the data, and we were able to get extremely accurate, I have to say probably world's most accurate fall detection technique. We have 2 of these devices, and they're on the head. Luckily, the head movement is a lot more predictable than the wrist, right? We always are flailing around our hand, but the head is more predictable. So when you fall, there is exaggerated motion coming from the head. And also there's the subtle differences between lying down and falling. And those signals, those features can be extracted with much bigger data set than we had previously. And now we have millions of these devices in the market, so we're continuously collecting data, and we're fine-tuning the model even more. So that's how we have been able to develop this. Any other questions?
Yeah, one question is that can the hearing aid helps in amplifying selective frequency range for the loss of hearing caused due to the exposure of heavy machinery for long duration?
Great question. Yes, absolutely. So it goes in 2 steps. First, when somebody comes and complains they have hearing loss, our audiologist or any other audiologist would do a detailed evaluation of measuring your characteristic hearing loss as a function of frequencies. The hearing aids are programmed according to your audiogram with really a measurement, making sure the compensation is very personalized to your patterns of hearing loss. For example, people who got hearing loss from loud machinery noise, they might have a notch type of hearing loss where they lost sensitivity to the mid frequencies versus age-related sensory neural hearing loss, which happens to be a slopey type of hearing loss at higher frequencies. That's why we measure every individual and then program the hearing aids to match the specific loss spectrum. On top, we use machine learning to make real-time determination about what signals to amplify. If it's speech, we recognize it and we amplify that. If it's noise, for example, a truck passing by or a vacuum cleaner noise, wind noise when you're outside, we don't amplify them. Hopefully that answers your question.
Yes, sir. Nicely explained.
Thank you. Okay, so let me take a couple of minutes on vision. Then let's see if you have another question. I won't have a lot of time here, so let me wrap it up in just 2 or 3 minutes. So computer vision and helping you to see the world better with AI. I am showing you a quote from 2010 book, from Zelinsky's book, when he was still at Microsoft. He had written, the dream of having a computer essentially recognize an image at the same level as 2-year-old human child remains elusive. That's 2010. And we all know with deep neural net, convolutional neural network, now we have machines with AI that can recognize objects better than humans can, right? And that transition happened in 2015, right? So what have we done here? My team has collaborated with a company in Israel called Orcam. And we have developed a pairing between hearing devices, like I showed you, and eyeglasses, along with a little device that has a powerful processor built in for vision processing that's stuck at the side of your glasses to help people who not only have hearing loss, but also have vision loss. They could be blind. So I want to show you a video to give you a sense of what this device does.
Text reading. A large rose tree stood near the entrance of the garden. The roses growing on it were white, but there were 3 gardeners. Face recognition. Jane. Money notes detection. $50. Product identification. Oatmeal squares cinnamon. Barcode. Sausalito cookies, 7.2 ounce bag.
Okay, so hopefully you got a quick sense of this device that we built for helping blind and visually impaired. I want to just quickly show you 30 seconds of a project at Stanford where this project is attempting to embed a CMOS sensor, an image sensor, into where your retina is inside the eye. And so this is still in ahead of human testing. But the idea here, if you've got macular degeneration that had damaged your retina, we would be able to restore vision in blind people. So it's a very promising project. Feel free to read about Stanford Artificial Retina Project. Ask me questions if you have any, because I do want to wrap up now because I'm out of my time. But I do want to see if there are other questions. Feel free to reach out to me at my Stanford email address. if I cannot answer all your questions now, but you happen to have comments to make, I'll take a few of them now as long as the time allows. I don't want to hold you back from your evening though.
As if I am not able to find out any other questions.
Okay, so
Okay, other faculty members, if anyone wants to ask. Okay, sir. So I think no question is there. Thank you, sir. Truly, the session was amazing and very informative. We came to know many detailed knowledge and the devices, whatever you had explained thoroughly. So now I would like to give you the memento as a token of love on behalf of all our, on behalf of our team, for your valuable time and the knowledge. So here is the memento. Kindly accept, sir.
thank you very much. I'm grateful.
Thank you. Yeah, thank you so much for the amazing talk.
Thank you and have a good evening, everybody.
Participants, I am sending the link for the feedback and the quiz. So kindly complete your feedback for this session and also attempt the quiz. And as per your request, we will give you some time in addition for this quiz to complete it. But do it by the honesty. Yeah, thank you. Thank you one and all. Chirag sir, anything else we have to announce to the participants?
No, just we have to share the link. I am sharing link.
I had
right
shared,
now.
sir, in a chat box.
Okay. Okay, you had said so. Uh, Session 2 quiz link I had said, and the session 3 feedback and quiz link is already said. So first of all, I am requesting you to attend the quiz 2, and then after you can start quiz number 3. And yeah, you will not get less time for this one. And I'm requesting you that please don't chat during the session, as it can be annoying to the speakers. Okay, so thank you. We are keeping the session open right now so that you can do the copy on of the links.
Yeah, and tomorrow session will start at 4 o'clock with the same link.
Yeah, link is there already in the WhatsApp group. So WebEx link will be different for tomorrow, and it is there in the WhatsApp group. Is it possible right now to share over here? Let me check. Nidha ma'am, have you shared the quiz number 3 link?
Yes, sir. In a chat, I had shared feedback as well as the day 1 session 3 quiz.
Okay.
I will again share. On
Okay, this is
WhatsApp group, you can also share. So maybe there are multiple messages coming.
okay. Let me check the quiz number 3 link again. Just a minute. Now you may able to see.